This is our second video on post systems in the Systems and Proof module for Foundations of Computer Science. We'll be picking up where we left off in our introduction to post systems and looking at a number of additional examples. Now, remember, the definition that we gave for a post system does not place any limit on the number of axioms or other inference rules that we have in a system. So we can easily define a post system with multiple axioms. And we're going to do one here that's related to a postage stamp problem, which you might have seen if you read Rosen's discrete math textbook. We say, for our first axiom, we say the number 4 is in our set. Our set is called P here. And then we say the number 5 is also in the set. That's our second axiom. And then based on those two axioms, we have a very similar production rule from the previous example. We say if x and y are elements of P, then x plus y is in P. So the first thing to notice is that even though this looks superficially kind of similar to our previous system, it gives us quite a different set. And the claim is that this is analogous to this postage stamp problem where we say that we want to prove that every amount of postage that is equal to 12 cents or greater can be formed using only 4 and 5 cent stamps. And in order to prove this, right, we'd have to show that every positive integer at least equal to 12 belongs to our set. And again, we'll return to this problem and its proof in detail in a later video on induction. But for now, we can just say that this is a completeness result that we're looking for. We're trying to make sure we have every amount of postage that is at least equal to 12 cents. We haven't really said anything about any kind of postage that we want to exclude. And so in this case, soundness is not really of interest. Just to wrap up our brief introduction of post systems, we'll take a look at 3 more examples of definitions of recursive objects that I think at least begin to suggest a little bit more complexity. So one of them is palindromes. And this, we're going to use a post system with multiple axioms for this. Our axiom 1 is that we have here the empty string is in a set. The set I'm writing as pal. And we say A is in pal and B is also in pal. So I've now implied that I'm using this alphabet AB. It's going to be my sigma. And I'm looking at the clean closure of that alphabet, and I'm looking for a palindrome, which if you recall is some string that is the same when read backwards and forwards. So those are my 3 base cases. And now I just have a production rule, which is that if x is in my set and y is in my set, then the concatenation of x, y, and x all together is also in the set. I've written parentheses here just to highlight the fact that when we wrote the definition of concatenation, we defined it as a binary operation. But remember, it's associative, and so this, without the parentheses, really would also mean just what you expect. So don't worry too much about that. And then the claim is that this set pal defines exactly the set of palindromes over the clean closure of the alphabet A, B. And that's not something we're going to prove right now, but it is worth kind of thinking about it because it's kind of an amazing fact, right? That any palindrome, any string that can be read backwards and forwards is somehow producible from this series of rules, these 4 rules. It may be interesting to try to write some out and then derive them, right, as an exercise. So far, all of our systems have had only one inference rule that isn't an axiom, and so we'll look at some that have more than one rule, and this is a system with multiple recursive rules. We start with an axiom where the empty string is in our set X, and then our first rule is that if X is in our set, then the string 1 concatenated with X concatenated with 0 is in the set. And the second rule is, again, if X is in the set, then 0 concatenated with X concatenated with 1 is in the set. Then finally, we have a third rule, and this rule has two variables. It takes an x and a y, and if x is in the set and y is in the set, then we have the concatenation of x and y is also in the set. So before we discuss what this is, let's try to sort of work out what exactly, based on these rules, is in the set. We only have one axiom, so we start always with the empty string, and that's going to be in our set x. And now we can choose which one of these rules we want to begin with. Well, if we want, we could choose R3, and we could just take the empty string twice, but then concatenating together would give us back the empty string, so we wouldn't see anything new in the set. So we'll move on instead and try R1. If we plug the empty string into our x, then what we're going to get out is 1 empty string 0, and that means the string just 1, 0 is in our set. And then if we do something similar, remove some clutter here, if we do something similar and plug the empty string into R2, then we would get out the string 0, empty string 1, which is just the string 0, 1. All right, so now we have some more things that we can go back and see what happens with rule 3. And we might take this first element 1, 0. If I add that in, 1, 0 here, maybe I'll use it twice, I end up with 1, 0, 1, 0. So that's in our string. Okay, so what does it look like I'm forming, right? Take a minute to kind of think about what the pattern is here. Of course, it's at the top of the slide, so if you have seen balanced strings, you kind of already know. But maybe, if you've played with this a little, you saw that there was some pattern here that each of these strings that I've made has a property that they have all of the same number of ones as they have zeros, right? And so that is what this particular post system gets us. It says for all y in the clean enclosure of the alphabet 0, 1, y is in my set x if and only if y has an equal number of 0 and 1s. And again, this is something you may want to play around with and try to verify. One thing that's especially interesting to think about is, in addition to soundness and completeness, do we actually need all of the rules in this system? In particular, do we need rule 3? What's it for? Can we produce all the strings we want without it? And in this case, no, we can't. We definitely do need it. We need it, for example, to create the string 1, 0, 0, 1. And so that may not be immediately obvious, but it's kind of worth deriving that string to see how exactly that rule is essential. Now, the last example of a post system we'll look at in this video is certainly the most complicated, but also, I think, by far the most interesting. So this is a post system that recursively defines the set of all well-formed formula in propositional logic. We'll have a whole unit on propositional logic later in this course, but sort of the key takeaway here is that we're able to define every well-formed statement just using this post system that doesn't really know anything about what the symbols mean at all. It just is treating them as purely syntactical objects. And the fact that we can do that and then reason over them in sort of a mechanical fashion is kind of the key takeaway from the course. So as I said, it's a little bit more complicated than the others, but given what it gets you, it's not that bad. So let's take a look at it. The first, we have two axioms, that T is in our set and F is in our set, right? So we have true and we have false. Those are in our set of possible statements. And then we have some inference rules. If X is in the set, not X is in it. If X and Y are in the set, then X and Y is in the set. Likewise, X or Y, same analogous rule. And likewise, X implies Y. And then we finally have we have to have some way of introducing variables into our statement. So we have some set of allowable variables, and we say if X is in that set, it's also allowable as a statement in propositional logic. And so this gives us all of propositional logic. Every statement that you can generate, you can make from this post system. And it's a little heavier than the systems we've seen before, but actually we could make it smaller, right? Some of these things you'll see later are not really necessary. We use the implication just for convenience, and we really only need one of the and or. We could make a very small post system that gives you the full expressive power of propositional logic. And again, what this gets back to is that earlier point I was making, that we can accomplish quite a lot by reducing a system to pure syntax and just treating it as symbols and then applying transformation rules to these symbols. And further, it turns out that the limit of what we can accomplish by taking this approach tells us something about the limitations of computers themselves, and the limitations of what we can achieve through computation. So now, before we conclude our brief introduction to post systems, I'd like to emphasize again that the way we're using them in this class is just as a convenient way of defining recursive objects, but they actually have applications that extend far beyond this. In particular, as we said before, they're very powerful expressively. They can express anything that any programming language can express. And their productions can define any computation, right? So they're very general things, right? And in practice, they're used as these deductive systems. And you can see some of these if you read through the binary. The Gensen and Hilbert systems are systems for deducing validity in propositional logic, an idea that we'll talk about a little bit later, although we won't use these particular systems. Just to give you an idea of something a little bit fancier that a post system might do, you can see here an inference rule that expresses modus ponens, which is the idea that if we have x implies y, if this statement, this implication is true, and that's in my system, in this case my theorem, and we also have x is in the system, then we should have y is in the system. So this is the sense of sort of following that implication and getting x implies y, right? This can be expressed using an inference rule as a post system. Just as a little side note, you want to notice that some kind of interesting quirk is that the term on the top here, my antecedent x implies y, is actually larger than y in the consequent. And this has some implications for when you are looking at inductive proofs later. In particular, if we were to do structural induction on strings, we frequently rely on them always getting monotonically larger as we continue. So this would actually break structural induction and require us to take another approach. That concludes our introduction of post systems. In the next video, I will walk through an example of a mutually recursive object called a rooted tree that's defined as a post system, and look at some what I think are non-trivial derivations so we can get some practice with working with objects that have been defined by post systems.